I'm Colin Fauché, and this is my submission video for homework 2 of mechatronics. First of all, we will measure the components of our circuit board and our resistors. I'll first measure the voltage of the 5-volt terminal. My measurement is 4.86 volts, so it's a little bit less than 5 volts. Then I'm going to measure the resistances of each individual resistor. Here's the two 220 ohm resistors. Resistor 1 measures in at 221 ohms. That's resistor 1. Resistor 3 is also 220 ohms, or it should be. And it's measuring in at 220 ohms. Resistor 2 should be 1,000 ohms. And it's measuring in at 999 ohms. Next, I will be calculating the theoretical values of the circuit that was given to us. This is what the circuit looks like with the 5 volts and exact resistors of 220 and 1000. To solve it, I first found the equivalent resistance by adding up the two resistors in parallel in series with resistor 1. Then using that resistance, I found the I equivalent of 5 volts over 400.33 is 12.5 milliamps. Then for each resistor, resistor 1, since it's in series, IR1 is equal to I equivalent, which is 12.5 amps. The voltage drop over resistor 1 is equal to 0.125 amps over the resistor, which is 220 ohms. The voltages over resistors 2 and 3, since they are in parallel, or will be the same, and it will be 5 volts minus the voltage drop, which will be both 2.25 volts. The resistances over IR2 and IR3 is the voltage over the resistor, which is 2.3 milliamps and 10.2 milliamps. Next, we will build the circuit. To start, I will be connecting this blue wire to the positive side of the battery, the 5-volt battery, and plugging it in right here. I'll take my first 220 ohm resistor, plug it to where it is in line with that, right here. I'm gonna put this red wire from the end of this resistor to this spot over here, in which I'll be putting in both the next two resistors. Resistor 3 and resistor 2 in line with this, so the current will be able to split as it should across each one. I'm putting them in to different spots to make it easier to measure the currents that flow through each resistor. So I'll connect this blue wire in line with resistor 3 and bring it to this point over here. I'll connect the wire to resistor 2 in line and bring it to the same point, so that the overall current from both of them can move to ground via this yellow wire. Okay. So now we'll start by measuring the voltage is over each resistor. So ideally the voltage over resistor 1 would be 2.75 volts. Touch them together. And it is 2.66 volts if you look at the voltmeter. .66. The voltage drop over resistor 2 is 2.18, where ideally it would be 2.25, and the voltage drop over resistor 3 should be the same, and it's 2.18 volts. Next, we'll be measuring the current in the specified spots. So the first current we'll be measuring is the current over resistor 1. In order to measure the current, we'll have to break the resistor. Break the circuit. So this is where I will break it. And we're getting a value of 11.85 or 86 milliamps, or ideally it would be 12.5 milliamps. The next spots we have to measure the current are over each individual resistor where it splits. So since the current will be the same right before the resistor and right after the resistor once it splits, I'm measuring it from the back end. So unplug one leg here. Oops. And I'm getting a value of 2.16 milliamps, or ideally it would be 2.3 milliamps. I have some fat fingers. Okay, now we'll be measuring the current over resistor 3. And I'm getting a current of 9.72 milliamps, where ideally it would be 10.2 milliamps. So that finishes the measuring of each part. So to compare it to the ideal circuit, the voltage was lower by 0.15 volts, and each resistor was pretty close to being spot on. So it is natural that the current was less than the ideal, because if you look at the equation, current is equal to voltage over resistors, and the resistance is about the same voltage as a smaller value. So it is consistent with what it should be given